Welcome to This Explainer. Okay, today we're tackling what's honestly one of the most fascinating engineering challenges in the entire world of robotics: getting a machine to successfully move from point A to point B. As humans, we totally take walking for granted. But for a robot, navigating gravity and terrain is an absolute computational and physical nightmare. So whether you're brand new to robotics or you're already an informed enthusiast, mastering the mechanics of movement is really that crucial first step in understanding how machines interact with the physical world. Let's get right into it. So how does a robot actually know the best way to move? Well, it's not just about slapping a motor on a chassis and hoping for the best, right? It's this deeply engaging problem-solution dynamic. To actually pull this off, engineers have to perfectly match a machine's physical, mechanical design to the specific, and let's be real, often unforgiving environment it's going to operate in.
Here's a quick look at how we'll break this down today. First, we'll look at the mechanics of movement. Then, Section 2 is all about wheels for fast and smooth terrain. 3 will cover tracks for navigating rough ground. 4 is legs, climbing like insects. And finally, Section 5 will wrap up with the Robot Zoo project.
All right, kicking things off with Section 1, the mechanics of movement. At its core, we're talking about locomotion. That's simply defined as the mechanical or biological method used to move from one place to another. And whether we're observing a wild animal out in nature or programming some highly complex machine in a lab, locomotion is literally the foundational concept for navigating the physical world. It's all about how you get around. Now, to actually make sense of the different ways robots achieve this, we're going to use a visual framework. We call it the Ways to Go mind map. This map logically categorizes how different types of terrain dictate a machine's structural design. See, you don't just build a robot and cross your fingers that it survives its environment. Instead, you study that environment first, and you let those physical constraints entirely shape how the robot is built to get around. It's form following function, for sure. Which brings us nicely to Section 2, wheels, fast and smooth. So wheels are engineered specifically for generating speed on smooth surfaces. And here's a pretty wild fun fact for you. Wheels are virtually non-existent in biology. Why? Because a freely rotating joint is incredibly difficult to nourish with blood vessels. But for machines operating in flat, uninterrupted environments, think a polished warehouse floor or a paved highway, wheels are the undisputed champions. They are incredibly efficient at converting energy straight into forward momentum. If we want to compare this robotic mechanical movement to an everyday tool, well, the humble bicycle is the perfect equivalent. Seriously, when you're riding a bike down the street, you are utilizing the exact same locomotion principles that engineers rely on when they program an autonomous delivery bot. It's all about minimizing friction and maximizing speed on a smooth, predictable surface. Simple, but super effective. Moving right along to Section 3, tracks, navigating rough ground. Now, what happens when the ground gets messy? That's where tracks come in, providing crucial stability and navigation capabilities for difficult, rough terrain. Unlike wheels, tracks drastically lower a machine's ground pressure. They do this by distributing the robot's weight over a much larger surface area. By spreading out that downward force, a tracked robot isn't going to sink into mud or sand or deep snow. That makes continuous tracks absolutely essential anytime the ground is uneven or unstable. Next up is Section 4. Legs, climbing like insects. Legs are a whole different ballgame. They are fundamentally designed for navigating complex obstacles and actually climbing over barriers. Unlike wheels or tracks, which generally need continuous contact with the ground, legs rely on discrete footholds. Think about it. When a robot hits a patch of random debris, steep stairs, or massive rocks, you really don't want to just roll into it. You want to step over it. And that's exactly where articulated robotic legs come into play, lifting the machine up to clear the barrier entirely. And this is where biological mimicry truly shines. Engineers are constantly looking to insects to solve these complex obstacle navigation problems. Take a robotic hexapod, for example. It uses the exact same alternating tripod gait that real ants or beetles use to remain perfectly stable while moving across completely chaotic terrain. Nature has literally spent millions of years perfecting this walking blueprint, and engineers are brilliantly adapting it to build better machines. It's pretty amazing. Okay, so let's tie this whole mind map together. The big takeaway: environments dictate design. Smooth surfaces demand wheels, just like our bicycle example. Rough, unstable ground
That requires tracks, taking inspiration straight from heavy machinery. And those complex obstacles require legs, directly mirroring insects. Grasping this connection is absolutely key to understanding the core mechanics of robotic locomotion.
And that brings us to our final part, Section 5, the Robot Zoo project.
The ultimate goal of this Robot Zoo project is for you to master the fundamentals of robot navigation through drawing and comparative analysis. Because honestly, the absolute best way to deeply grasp these complex engineering principles isn't just listening to me explain it, it's actively creating it yourself. When you physically draw out a robot's design, you're forced to critically think about how its specific mode of locomotion perfectly suits its intended environment.
To get you started, here are a couple of fantastic, animal-inspired jumping-off points for your design. You could consider a six-legged insect bot, which, as we know, would be perfect for stepping and climbing over a rocky, uneven landscape. Or maybe a rolling turtle bot. That one could utilize smooth wheels safely hidden under a protective shell, explicitly designed for zooming across flat, fast warehouse floors. These concepts are really just here to spark your imagination for your own creative drawing.
So, I'm going to leave you with this provocative thought. What animal will inspire your robot design? I want you to think deeply about the different environments around you. Think about how specific animals traverse those spaces, and then imagine the mechanical equivalent to make that happen. Will your machine use wheels, tracks, legs? I really hope this explainer has left you energized and motivated to boldly explain exactly how your own animal-inspired machine moves. Keep learning, keep exploring, and start designing.